All right. Well, again, thank you very much. Very excited to be here. I slept for 3 hours last night. I have 2 little babies, so I may start, wondering about and not making sense at some point. Just stop me or give me a look, and then I'll say, okay, yeah, I'll go 2 steps back and start again. Now, the first thing I wanted to say is this title. Whoa, where's the pointer? It doesn't work. This one, right? No, because, yeah. So anyway, Bruce Schaefer, who most of you will know as well, suggested this title for a talk that I had to give in Canberra recently. And I guess for that purpose was great, but I wanted to change it from the beginning to this one because we are just touching the edges of what our final goal is. Now, do you think that will work? No, exactly. It's a screen, yeah. So, yeah, it's a fancy screen that doesn't allow you to, yeah. So I'm going to use my finger. The real PowerPoint. So, yeah, so let's start with that one. Being a geophysicist, usually I've been following the approach that can be considered or associated with the great John F. Kennedy. Don't ask, what geophysics can do for you, but the opposite. Now that works well with geophysics audiences, but not so well with other type of audiences. So I also have my Trump approach to this. And this works really well with non-specialist audiences. It's fantastic. You just show me the money, right? So I've been training myself to also do that. But today I decided to do something in between. And at the risk of losing you, or most of you in the middle of the talk, not because of the content, but because I'm going to bore you, or I'm going to be all over the place. But let's give it a try. Just bear with me. So, sorry, I'll go back. There you go. Good.
From the States, I gotta have a picture of that.
Oh yeah, go for it. They will love me. No more invitation to AGU. So, not exactly, yeah. This is a slide that I use again for that talk, but I use it for teaching as well. I'm amazed when I think about, the distances that we've been able to cover and the actual fields that we've been able to, well, not we, but very intelligent people that have been working on space sciences, to really measure, the fields that we've been probed directly with man-made probes. Looking up, it's always very exciting. A lot of effort has been going on, and exploring now actually the outer space. In outer space, I really mean outer space because Voyager 1 is actually reaching the heliopause as we speak, and it's reaching the intergalactic space. Sorry, interstellar space, and it's still transmitting. So when I think about it for 10 seconds, I say, wow, this is such an amazing achievement. Now, the third rock from the sun, when we compare that to what we get when we look down and what we've been able to directly measure, it's a little bit disappointing because so far we've been able to go around 12 kilometers down to the center of the Earth. That's when you compare it with 6,371 kilometers, which is the radius of the Earth. That's nothing, right? If the radius of the Earth was 100 meters, which is the size of a block, the actual deepest borehole will be less than 20 centimeters. That's all the rest, the 99.8 meters that we're trying to characterize we had to do it indirectly. Right? And to some extent, we've been victims of our own success because the community has been very successful in imaging and characterizing the interior of a planet. So a very beautiful example from seismic tomography, of course. Seismic tomography has provided us with wonderful images and information about how complicated and heterogeneous our planet is. And this is just an example, a relatively recent one. Now, you don't have to go very deep. My interest usually is in that little area. Basically, the shallowest 400 kilometers. So yes, you can call me a shallow person, and at least a shallow scientist, for sure. And but that's, I mean, the reason for that basically, to me, is because it's in this area actually where I can see most of the expressions of plate tectonics. And we are very lucky to have plate tectonics in our planet. That's the reason why we're here in the first place. And this is where we see all the action, seismic activity, volcanism. So that's, I'm naturally interested in that area. It's also what causes a lot of grief. And we've been recently knowing about this firsthand. But again, it's not only seismic hazards and volcanism that interest us. Of course, this is related also with the places where we can find the resources that we need to sustain the society that we love and that we're used to it, which is very expensive when you put it in terms of natural resources that we need. So that is my region of interest. And I don't have to go deep into the Earth to see the actual truth, the fact that even in this region, the Earth is very, very heterogeneous at multiple scales. So this is a diagram from a petrologist, and I don't necessarily agree with this, but I like the concept of showing a continental lithospheric mantle, which is not the typical green rock that we've been trained to think. Even when I was studying, the lithospheric mantle to us was a green stuff that you only needed a coefficient of thermal expansion to characterize it, and that was enough. It's good. But petrologists, of course, decades before that, they knew that the continental lithospheric mantle is bound to be very heterogeneous. It's a very old piece of the Earth, evolving for billions of years and subject to a lot of different processes. So the complexity, it shouldn't be a surprise. You can see that in outcrops. You can see that very clearly in xenoliths as well. The chemical and thermal structure of the continental lithospheric mantle, again, shouldn't be no surprise that it's complicated and highly likely in many places totally uncorrelated. I mean, it makes sense also from the point of view of simulations. These days we can run simulations to model certain processes. In this case, for example, the collision of a continent with an arc. And the complexity that you get at the end of the process is obvious, and this is only one process. When you consider that, of course, internally there you have processes acting at a totally different scale, in this case the microchemical and microstructure evolution of it, where grain size depending on the local thermodynamic conditions can grow, can anneal, or they can get smaller, and depending on what they do, the physical properties of the materials will change, and the chemistry that you will get when you start melting this rock at different stages is also very different. So we've been, for some time now, we've been wondering about these complexities, and at the same time when you produce melt, and melting arguably is the most important process in the evolution of a planet. The mass transfer and the energy transfer associated with that process condition pretty much everything that happens on a planet. So when you have that, the recognition, therefore, that these processes are not only multiple, at least a two-phase process, because you have two very defined phases, the solid and the liquid, that they will be reacting all the time and exchanging chemical elements. You need to find ways of at least think about these things and hopefully be able to characterize them, because that's what gives us the opportunity to predict what the rocks will do in terms of the evolution, for example, of the mineral composition, or the actual chemistry of the rocks, or the magmas that are generated during the different processes. But of course, this is complicated. It took us a long time. It took us actually more than 5 years. And I think in these forthcoming publications being recently accepted, at least we managed to tackle some of the major problems in terms of the math and the governing equations. Not complete, it's never complete, but I think it paved the way to make some things easier in the future, to really work with this idea of a multiple phase multiple component, chemical component, reactive flow inside the Earth. So all these, of course, are very 4D problems. You know, we live in a three-dimensional world, some will say, and plus time. So they work, of course, on multiple scales. Now, this is my personal opinion, and I'm biased here, but I still think that the multiple or the multi-scale nature of the process that we're interested in is a very unexplored field. But it is in the connections of these multiple scales and the couplings between multiple scales that actually give us a true understanding of how things work and allow us to connect different disciplines and different observations. But it's of course, very hard. Does it make sense to work with all these complexities at the same time? Well, some people may say no, and some people may say yes. I'm a believer that science evolves very well with separating things in multiple smaller pieces that are easy to understand, and that's great. I mean, that's a fantastic thing. Sometimes I try to do exactly the opposite as a complement, not because I'm competing or anything, but sometimes I try to put things in the context of complexity, that the world we live in, you know, the system we're studying are complicated, and perhaps we should do something of or try to achieve a similar complexity as well in our studies. You know, I have a great quote that I always use from Richard Feynman, that at least is assigned to him, that says, you know, what I cannot create, I don't understand. And I think it's clear what he meant. I mean, particularly in the context. If you're not able to create it either in your computer, in your lab, you know, you're not really understanding it. So if we want to understand a complex system, perhaps we should spend a little bit of time trying to do some complicated things. How about for the present day situation? And what I mean by the present day situation, if the Earth has this, you know, multiple scale processes, it will be very good if you could image at least some of them, because that will give us a little bit of information, ground truth, to test the temporal evolution of these processes. And this is what I want to focus on today, because of course otherwise there are a lot of different talks here. But I wanted to focus then on how much can we push our techniques, our methods, our data in order to try to image some of things as they are occurring. So this is the topic for today. So let me start with perhaps what can be considered a traditional approach. In a traditional approach, first of all, we will think that we understand, you know, thanks to people like Greg Hausman right here, we understand the dynamics of the large scale dynamics of the Earth. And we've also been very successful with techniques like seismic tomography. So in this case, I'm just showing the Colorado Plateau area and one study, relatively high resolution seismic studies, a transect that they use in order to get a seismic image. This is an image of anomalies in wave speeds. So basically red is low velocity, relative low velocity, blue is relative high velocity. And with this image, with something like this, which is what usually we get, then you can hypothesize and say, well, as these authors did in this paper, well, they said this looks like a small-scale convection, and let's try to model forward scenarios, basically with trial and error, using thermomechanical simulations with a structure that they think was representative of the lithosphere. And they try, you know, trial and error, change the parameters here and there until they get a synthetic seismic anomaly or seismic tomography from these studies that they can say, well, this looks like that, therefore there is evidence for small-scale convection in or beneath the Colorado Plateau. Of course, you have to have a lot of faith to say that that actually is or is a good representation of what you actually see, but I think it's a very good starting point. The question, of course, is, or at least in my opinion, it will be very nice not having to do this. It would be very nice to let the actual data to tell me what's going on here instead of trying different configurations and try to get one that matches the actual observation. This extends, of course, to other observations as well. For example, this is a relatively recent seismic model of the lithosphere, and these are the observed potential field data, in this case, free air anomaly, the geoid, actually the lithospheric geoid, which is a filter geoid, and the vertical gradient of the acceleration of gravity. So these are observations. These are the predictions from Litho 1.0. And let's be fair, Litho 1.0 was never really thought to try to fit these observations in particular. But having a model that actually doesn't fit absolutely anything, I mean, by orders of magnitude, is also a little bit shocking, because we're talking about a reference model. We should be able to do a little bit better, perhaps. There is another problem, an associated problem. This is a paper written by Nick Flemont. Most of you will know as well. You used to be in Sydney Uni. Where with the problem of dynamic topography, everybody talks about dynamic topography these days, is basically what's the component of the topography that is associated with the dynamics of the mantle? You can call it like that. Everybody tends to get relatively consistent spatial distributions based on what we know from seismic tomography, but the amplitudes can vary a lot. And it's a problem. That tells us that there is something that we are not really understanding there. So the premise of the work that I'm going to show now is extremely simple, and it's been known for a long time. If all the methods that are used as proxies to obtain information about the physical state of the interior of the Earth, when I say physical state, I mean the temperature, composition, the pressure distribution. If all the methods that we use as proxies are correct, then all of them in the end should be compatible. And all of them should pass the test that they should explain not only one type of data set, but all types of data sets. That's the ultimate test of a model. So the premise is extremely simple. The problem, of course, it will take my life and probably the life of other people to get something decent out of it. Because the first thing that you realize, of course, is that you need to put together a whole bunch of different things, or at least consider them very seriously before you can come up with something that will make sense. Some of these disciplines and the information that come from these disciplines can be considered fundamental. Some of them are ground truth. Like, for example, the information that we can get from geochemistry. This is data, right? However we interpret it, this is an observation. The same thing with seismic information or geophysics information in general. Now, the combination, after thinking about this for some time, we decided to go for what is known as a probabilistic, multi-observable, and internally consistent inverse framework. And this is a mouthful. My wife told me today when I left, remember not to use fancy words. I'm like, I'll try my best. But so what is this? Well, probabilistic, let's make it very simple. The problem at hand is actually statistical in nature, in the sense that the data that we usually have to work with is always incomplete. So to begin with, we have incomplete data. So when we derive a model that is consistent with incomplete data, it's obvious that we're going to have, highly likely, many different models that will be consistent, but all of them at the same time are going to be different. So which one is right? This can be addressed in a very natural way if we use a little bit of statistics, or at least what we know as the probabilistic approach to an inverse problem that I'll explain in more detail later. Why multi-observable? Even simpler. Different observations constrain different parameters of the system that we're studying, and it's as simple as that. So, of course, since we are trying to constrain the physical state of the planet, we need a lot of information that provides sensitivity to temperature in one hand, but others will need to provide sensitivity to composition and others sensitivities to pressure. Pressure is usually not a problem, but we need a combination of them. And why, and this is key, why internally consistent? It has to, so you cannot adjust the properties of your model to fit one observable without affecting all the other ones in an internally consistent way. So if you are fitting gravity and you say, oh, you know, it will be great to change the density in my model here because then I will have a better fit, then that change has to be reflected in consistent changes in all the other observables. How consistent? Well, we chose to use thermodynamics. Why? It's good. It works. Right? That's the one thing that you can trust. Not how to use it, but thermodynamics works. Right? Otherwise, we're in trouble. So the first thing was to say, well, we're going to free ourselves from the traditional inversion approach, and we'll work with what I call a simulation-based approach, for lack of better terms. It's not really good, but this basically means that from now on, when you think about the inversion results that I'm showing you, the inversion method, you have to think about, we try real simulations. So it's almost more like working with a thermomechanical simulation, but in the context of an inverse problem. An inverse problem, you have data and you need to get the model. The forward problem, you have a model, you predict data, right? So we use both of them in a two-way path, but the method is mostly related to a thermomechanical simulation and not so much to the traditional parameterization used in a seismic tomography problem, for example. Now, thermodynamics, there is one good thing about it, well, several good, but for us is the critical aspect is that if you think, there are many ways of representing this information, right? That's one of the problems with thermodynamics. But in this case, this is known as the master equation of chemical thermodynamics. And it says that the Gibbs free energy of your system is a function of pressure, temperature, and composition. These are number of moles. If you are able to define the free energy of your system, whatever your system is, can be a little piece of mantle, can be a glass of water, whatever it is, if you're able to define its free energy, Gibbs free energy, all of the properties that control the dynamic, the physical behavior of your system, coefficient of thermal expansion, density, seismic or elastic moduli, thermal conductivity, all of them can be obtained thermodynamically consistent, in a thermodynamically consistent way, via derivatives of that free energy. And the beauty of this is the fact that you cannot violate fundamental laws of thermodynamics. And that's a good thing. There are people that don't believe in this. But luckily enough, there are not many in the scientific community. Now, how do we do it? Well, the process is very simple. Everybody, I think, will be familiar with seismic tomography these days. That's great. You usually have one type of data set, sometimes two. For example, in this case, dispersion curves, or actually will be the travel times, but what we usually end up inverting is dispersion curves. And you run an inversion, which again, for lack of a better term, I call a parametric tomography, because what you end up with is a model of the Earth based on physical parameters, in this case, the seismic velocity. So you know the seismic velocity structure of the planet. You can do the same thing with electrical conductivity, right? But these are the physical parameters. That's why I call it the parametric tomography. The thermochemical tomography, the idea of a thermochemical tomography is to bypass this, make use of all we got, basically make the most out of the data, which is always very expensive, and invert directly for physical states. So directly, you get a model of the Earth based on the pressure distribution, the composition inside the planet, the temperature structure inside the planet. If you manage to do that incidentally, this one becomes a byproduct, a free byproduct, because it's always there. You always can show your tomography to seismologists. Is the only thing that they care, right? So it's a very convenient thing. And I'll show you later why, but it's a very convenient thing, but this is not the end of the goal. The goal is here, but this one is always there. You can pull it out of your solution, whatever you want. But arguably, this tomography, I don't want to say better, but well, I'll say because I can't find a better word now. Arguably, it's a better tomography because this is a tomography that is consistent with not with one set of data sets, but with a whole bunch of data sets. So it's not only fitting the seismic information, but it's also consistent with everything else. That sounds great. Unfortunately, there is a long list of problems to deal with. And this is by no means an exhaustive list. These are some of the ones that I consider important, enough to spend some time trying to tackle them, or at least to get some answers to how to deal with them. If you want details, there are 93 pages of details, which of course we're not going to cover here. So part 1 is 33 pages, part 2 is 31 pages, and part 3 I think is 34 pages or something like that. Of course there are details, and there are a lot of technical details, but we want to skip them. I prefer this figure, because this figure shows very clearly we have a data vector, and this is the actual data vector that we can use today. You combine that with the theory, the physical theory, the geophysical theory, and then you obtain your models. Right? Now, these are the models, of course, that you will publish, and this is what everybody wants to see, nice figures. I think I have a better representation of what the models actually are. They are distributions over possibilities. So because this is a probabilistic approach, I can't get a single model. I get an entire probability distribution of potential models. Some are more likely than the others. But in the end, all of them are compatible with data within uncertainties. Some of these problems, and this is where I spend most of my time, to be honest, is working here in this area. Some of these problems are trivial. There are recipes to work with them, fantastic. Some of them, no. For example, Stokes law. As Greg will know, Stokes law in 3 dimensions in spherical coordinates is challenging, it's tough, it's numerically expensive, computationally expensive. I have to solve all these problems at the same time in less than 1 second if I want to achieve this. And that, for those who knows how that is done, how the Maxwell's equations in 3 dimensions are solved, or how the travel times for the body weight tomography are solved, these are computationally challenging problems. How can we solve them in 1 second or 2 seconds tops? All of them at the same time. Well, here again is where I spend most of my time, and I'm just going to give you a hint for one of them. This is a typical problem for Stokes law. And what is a Stokes law? Stokes law is what dictates how the mantle is convecting, how the interior of the Earth moves, if you want. That's what we call Stokes law, right? The mantle flows. That's a typical problem. No interest in the details there. The interesting thing is that there is a certain approach that is known as the reduced basis method that kind of simplifies the problem, and it allows you to control how much you want to simplify it and how much accuracy you're after. So here's the trade-off. There are no free lunches, right? If I want a very accurate simulation, forget about it. Run your simulation. But if I can afford a little bit of uncertainty, maybe because the data that I'm using to constrain that flow is already uncertain, then what's the point? If I have an uncertainty this big on the data, what's the point of having a perfect run? Because the run can fit in all these places, right? So I can afford a little bit of uncertainty. If I can do that, I can start working with these methods. And the important thing here is that this is the computational cost of running simulations and without RB. Basically, this is a straight line, but the scales are different, right? But this is a straight line, a one-to-one correlation. If I want 50 solutions, I have to run 50 simulations. And if I want 150 solutions, I need to run 150 simulations. This is what I need with reduced basis. So now, if I'm after 800 solutions, I only need to run 35. And this is very silly. Well, it was preliminary. I need to update this one. But this one actually reached an asymptote, as you can imagine. And I never have to solve more than 50 or 100 simulations to have millions of solutions. And all of a sudden, that opens up all the doors. Because now I can afford to do this probabilistically. So this is actually a very good thing. This guy actually, this is like a 20 years old picture, by the way. This guy's very famous online. He's like 20 years old now, and he still poses like for the same, yeah, has the same pose, but yeah, apparently that was a totally real picture, no PowerPoint there, or Corel Draw, or Photoshop, something like that. So yeah, sorry. Again, the overall message is, now with 5% of the computational cost, I get the entire spectrum of solutions. Basically, 95% of my computational cost disappears. So now, quick examples of how this works. So we try this on this beautiful area that will never work again in my life. The Colorado Plateau and the Rocky Mountains. Very interesting from many points of view, but for us it was very good because we basically could saturate the data vector. In other words, we had all the data that we wanted. And it was an interesting area in terms of, the heterogeneities and some tectonic problems. Now, I never knew that there were so many problems, otherwise I would have never chose that one. But this is just an example of data. We had for the first time this fantastic new data set, which is the gravity gradients from satellite missions, the European Space Agency satellite missions that provided this information. We had very good seismic information from surface waves. We have body waves. These are the stations actually that we use for collecting the seismic data. And we have gravity, geo, and so on and so forth. So we basically have a lot of information here. These are just some examples. This is what you would show to, for example, a seismologist. These are the tomographies that we got. And you can compare this, for example, with a purely seismological approach of surface waves. Actually, in this case, it's a joint surface waves receiver function study, by Weiss and Shen. It's the Colorado group. So, visually speaking, this is a transect in between these two. It's 125 kilometers, so it should be somewhere here. But of course, the patterns are very, very similar. You can draw a better comparison by analyzing absolute velocities. Here, the blue are their model, and the red ones are our solution. So I don't think there is a problem here. And if it was, I wouldn't be showing it, because then it means that either them or I'm making a mistake, because the data that we're using is the same. Actually, we use the same data. And there's some examples of, we also fitted the receiver functions. These are fit to the dispersion data. Believe me, in terms of data, we were doing okay. But of course, that is not what we're after. This is what you use as a control if you want. What we're after is the physical state. So things like, I want to know the temperature distribution. I want to know where, if any, partial melting occurs. I want to know the crustal thickness. I want to know the temperature distribution, and I want to know the composition. So these are just examples of things. And again, there were some controversial things, but to some extent, this is what you would expect from all we know, right? So I don't think there were major surprises in these results. As a matter of fact, it was rejected in Nature by basically one reviewer said, well, there are no true new results. And we knew about this. And you know what? So I'm thinking, yeah, true. But the one thing, for example, and of course we're talking with Steve about this as well, this was a little bit of a problem, because this is a very, very thin lithosphere. And believe me, there is no way I can make it much thicker. But then, of course, we're talking to people, there are people that prefer a thicker lithosphere there. So I'm wondering. I found a recent study with the Cambridge group, and they basically use thermobarometry and geochemistry, and nothing more than that, on these samples. And they got exactly spot on the level that we predicted. Now here there is no explicit information from geochemistry. This is all geophysics and geophysical data. So, but it remains to be proved, I guess, that this will, it will have to pass the test of time, right? And if there is other evidence against it, of course, we're going to have to review what we're doing wrong. But in general, things were more or less okay. In this case, this is the famous four corners, and we had some very good thermobarometry from data. And since this is the least perturbed area of the area of the Colorado area, because all of this, of course, as you can see, is very hot, and is, as you will see in the other slides, has been perturbed very recently. But this one still remains kind of the core. So if there is one place where your xenoliths will kind of reflect what you see now, it should be somewhere there. And actually, that's the case. Those are xenoliths from thermobarometry, and this is the distribution that we get for that particular point. So that's about temperature. What about composition? Composition, in this case, I'm just showing the composition in terms of the magnesium number, which usually people, they say it's a measure of depletion, basically how much melt you extracted from the mantle. The reality is it's a two-way trip, because it can be depletion or it can be refertilization. By depletion, you extract melt, but then if you bring melt in, you can refertilize that mantle. And it works both ways. So when we got these results, I was a little bit concerned, because what I was expecting is a beautiful, highly depleted, very buoyant core in the Colorado area. And then I got just a little bit, but then I got very fertile lithosphere in this area. And this is the lithospheric mantle, which was very thin as well. And so it took me, I had to talk to my colleagues at Macquarie, and then they gave me the push to pursue this, because they said that they had actually very good evidence from xenoliths that all this area has been refertilized. This is an area where melt created in the lithosphere percolated through the lithospheric mantle and refertilize everything. So they have very good independent evidence that that has to be a refertilized piece of mantle. So another nice coincidence, so we decided to have a go. We also collected samples where we have good thermobarometry and good compositional data, and we compare it with our results, and here you have the observed distributions and the predicted distributions from geophysical data. And here I was disappointed, because as some of you know very well, I work with Bill and Sue for some years now, and they always know the truth before you try it, right? So they told me this already, and they said, we knew this. So I was expecting that at some point I would prove them wrong, or at least create controversy, but it didn't work in this area. I got basically the same distributions that they had, so they knew what the composition was. Okay. I'll show you another example quickly where this didn't happen. Now, this is the same area, the Colorado Plateau, showing a 3D diagram of the temperature distribution. Now, if you remember what I showed you before, this was a transect somewhere here, and this was the tomography. Now, all of a sudden, we have our tomography, we have our thermochemical model, but I can see now what's going on. I can see the temperature distribution that is consistent with this, the data that these people are using, well, not exactly the one, but very similar. And I can have a better interpretation of what may be going on here. As a matter of fact, by solving at the same time the Stokes flow problem, I retrieve the actual flow associated or consistent with all the data sets that I inverted for. So I don't have to be trying, doing trial and errors, trying to get something that explains that information. This comes now from the actual data that was used to create an image like that. And interestingly enough, we found something that people knew about already, which is that, yeah, apparently there is small K convection at the edges of the Colorado Plateau. There are a few curiosities that I will avoid now not to mention, but it was good. It was really nice. Now, we tried this in other places. In China, it was really, really nice because although we couldn't run the full three-dimensional model, saturated with data, we got some decent data as well, and we could feed one of these inversions. So this is the Eastern North China Craton. How am I doing with time?
Probably another 5 minutes, maybe.
Excellent. Yeah, that's all I need then. The East North Korean Craton and the transitional region, and then the Ordos block. Now, everybody knows that this area is extremely anomalous because this is a craton, but the lithosphere seems to be very, very, very thin, and there is good evidence from xenoliths that it's been refertilized, and all the lithospheric root is being detached, which is not common for cratons, right? But this is a very well-studied region. So running these things, we managed to image the actual flow coming from the transition zone, which is associated with the Pacific plate that stalls at the transition zone in this area. This flow, which is a force flow, is interacting with the lithosphere, particularly in the Ordos block, is being deflected to areas where the lithosphere is very thin, and it's actually in some places creating a return flow as well as it pushes through the asthenospheric mantle. I'll skip the compositional aspects. We got some data for composition that we can compare with data. And the only thing I'm going to say is, in most places, we were getting consistent results. But then we found something like this, where the information say this is entirely refractory. You're telling me the geophysical information was telling me that everything is fertile. And what happened here, again, I thought, well, this is a point of discussion. This is where we're going to have a discussion with Sue and Bill. But then there was no discussion because they say those xenoliths are 60-something million years old. These ones are 6 million years old, 4 million years old. So what you're seeing there is the remnants of the actual lithospheric root that existed at one point, and now it doesn't exist. So now you're seeing this. And that was the end of the discussion. Now, what is going on at the moment? Well, first of all, we're trying to do this globally, and this is a fantastic project because it requires hundreds of thousands of CPUs. And so we don't know if we're going to be able to do it. And it's the largest probabilistic inversion ever attempted anywhere. The astronomers, the astrophysicists have run simulations up to 70 to almost 90,000 parameters probabilistically, not deterministically. Everybody can do that. This one is at least 1 million parameters. So hopefully in the next 5 years, we're going to be able to tackle this one and have that sort of results that I show you for the entire world. And the other thing, of course, what's for the future, for my students and the rest of my career, basically. I'm very interested in pursuing, again, the formal combination of inverse geophysical theory with these 4 critical components, and basically trying to gap a little bit, to bridge the gaps between the scales, different temporal scales and spatial scales of processes that we can observe, or at least that we can infer from surface data, which is the one that we can access. So you can run simulations, but these simulations at the same time need to be taking into account the actual microscopic evolution, because actually the microscopic evolution controls the macroscopic evolution, and we're trying to understand how. This is not an easy problem, but we're trying. And once you have that, it opens up possibilities to really interpret data or feed data, or I don't like the term feeding, but at least make sense of data that otherwise it's very hard to explain. And this is something that we've done with Chris Gross, and it's also in present Journal of Petrology. So again, does this make sense? I don't know. To be honest, I don't know. But it's very entertaining, and as long as I have blood in my veins, I think I will go for it. So thank you very, very much.
Thanks, Jeffrey. We might give it 5 or 6 minutes for questions. Anybody got any questions? Anthony?
Well, JC, I think what you do is completely nuts.
It is.
To quote the Instagram ads that I grew up with, you only get out what you put in. So
yeah.
How does data quality affect the overall quality of the models, especially on something like going from a Colorado Plateau, which is relatively small, to a global scale model?
Yeah, fantastic. I mean, yeah, we have a different way of putting it. It says sheets in, sheets out, right? Yeah. So, actually, that's my bad pronunciation, but it's better in this case. But yeah, absolutely true. The one thing that actually we are trying to acknowledge is exactly that, is the uncertainties in the data and how that translates to uncertainties in the model. So all the models that I showed you, in the end, are a statistics of the probability distributions that we get. A statistic is, for example, the average or the mean. Yeah? So I can play around with the mean, I can play around with the median, I can play around with the standard deviation, but in the end, the result is a probability distribution. It's a family of solutions that are consistent with the observation, taking into account the uncertainties in data and in the model. And I take pride on the parts of the model because most studies will not really care about the uncertainties in your model. Basically, the assumption is, my model is perfect. I compute travel times perfectly. I compute dispersion curves perfectly. There are no errors here. And that's rubbish, right? So you need to take that into account. It's very painful, but you can do it. And at least you can do it to a certain extent. And we've been working on that one, and these simulations include that. For example, the typical assumption is Gaussian noise. Everything has Gaussian noise. Why? Because it's extremely simple to work with. Everything is a bell, curve. Rubbish. Show me a numerical model that will have white noise. No, it doesn't exist. Everything is extremely biased and very systematic. So you need to address those problems. And there is a lot to be done, but I think at least we've done something about it. Yeah, but we consider these things. And again, rubbish in, rubbish out is the fact. Some of these data sets are more certain than others, and they try to compensate one for another. But yeah, you have to have good data, that's for sure. And the one thing that we do, for example, when we publish these things, is we have a MATLAB software that takes the. No, I have to go back. But I show you one example where all the distributions. So this MATLAB software basically takes the output of the inversion and allows you to visualize the actual distribution. So I can publish the means, I can publish the average, I can publish the median, but then everybody can access the full distribution and know where the distribution are Gaussian, where they're no Gaussian, where they're double peaked, and at least you can explore that you know. So yeah.
Thanks for an amazing talk, JC. I have a question about the global, I guess, plan.
Yeah.
It sounds like from your method you could attempt to recover the crustal lithosphere structure. But one of the things that I've always wondered is this radial structure of the Earth, the preliminary reference Earth model, for example. Do you think that your approach could help us refine that radial model assumption?
I don't think we're going to be able to come up with a better reference model. The ones that we have are very good, right? And if we have something significantly different, then I'll be worried, because these guys have been doing a really good job at putting the reference model, seismologically speaking. What we are hoping for is to have a reference thermochemical model. So what we're trying to publish, hopefully at some point this year or next year, is a reference model that explains all the data sets at the same time. So this is a reference model that somebody can use when doing gravimetric studies, and start with that and try to refine. Somebody who's doing body wave tomography, and they can start with that and then refine it. Somebody who's doing electromagnetic studies, you know. So that's one of the aims, have that sort of reference. That one, we have it already through linear inversion. So it's not a probabilistic. And why do we have to do it like that? Because we don't want to run things like crazy. We want to start from somewhere that actually makes sense. And the other one is that the idea of this is that you can use it anywhere in the world. So if you decide now to go to Australia, like one of my students now, you always have problems with edge effects when you are working. For example, Stokes-Ford, do I solve it in a box? Well, what's going on with the rest of the world? Gravity. Do I solve the box? What's going on with the effects, you know, of the slabs that I have here? But with this reference, now we found a way of compressing that information. So now the code, you can put your box anywhere in the world. The effect of the world is already included all the time. So boundary effects are not a problem anymore, as long as your reference is okay. Right? Now, for solving the final problem, I don't have solutions. I'm sorry. I put a DP last year, and hopefully, if we get it, we need to tackle the actual problem of computational efficiency to make this a reality.
I really like your approach, JC.
Thank you very much. That means a lot from you.
There's a lot in it. But it is very daunting in a sense. And if I take, for example, the issue of the rheological law, which goes into the Stokes law, we don't actually know those laws very well.
Nope.
So, you know, do you envisage that the kind of process that you're doing might actually deliver a better representation of those laws, rather than the ones that are the stock models that are used these days?
Look, the short answer is that's one of the aims, to basically invert for the viscosity structure based on what the data is asking you. We are a long way, I think, because all the methods that I showed you, we managed to make them work for Newtonian types of deformation, or Newtonian laws. Which at the scale that we're interested in, they may give us some information, you know, from some first order information. We haven't managed to make them work for nonlinear, although we know that it can be done, but we haven't been able to make it as efficient as we needed. But the final idea, my final idea, is to be able to obtain viscosity as the three-dimensional distribution of viscosity as an output of the model as well. But I need a forward, I need a forward connection there. And that forward, I mean, I can invert for the parameters, right? But the forward, I need to assume some sort of constitutive law, if you want. I need to decide in advance whether this is going to be Newtonian, how many parameters I'm going to have. Or I can simply, like the test that we ran at the beginning, I can simply assume a viscosity at a certain node, and then I just play around with the actual viscosity. But the viscosity is what enters the forward problem. Again, in the forward problem, it requires a law. How far we can push it then, I haven't given too much thought to the actual problem, but I think we could potentially come up with something, that, very quickly, in the Colorado Plateau, when we published the result, I didn't want to say anything about this, and the reviewers forced me. And what I said basically is, we didn't invert it for viscosity. But we clearly found out that if we moved away from certain ranges in the allowed viscosity, we couldn't fit anything. And it turns out that those ranges were, not surprisingly, between the ranges that everybody has been trying to get, for the past 30 years. Is the asthenospheric material, if I remember well, is of the order to the 19th. And that was the thing. Some places will go up to the 20th, but it was in that order. If I move to the 22nd, for example, impossible to fit data. If I move to the 18th, it was extremely hard, although in some cases I could. But yeah, we need to think more about that. It will be an interesting problem.
It does kind of raise the idea that actually there might be parts of your parameter space that really are inaccessible.
Yeah.
Whatever data that we've got.
Yeah.
But you can't actually say with any kind of certainty what we've got down
Yeah,
there.
absolutely. And when you look at the distributions of this particular study, for example, the VPVS in the crust, for example, was terrible. It was terrible. And I published those distributions so everybody could see, we just didn't have sensitivity at that point. We improved it in the second publications, but at that point it was awful. But there are some other parameters that were really well constrained. So how much you can push these things, again, they need to pass the test of time in the sense that more people come and try, and if things converge, we either are all wrong or we are getting somewhere. So yeah. But it is, the people that are using it always, and that know me well, like Alan Jones, they say, your approach is terrible. It's too hard. It's too hard to work with because, again, when I get the terabytes of information out of it, I have to spend 6 months exploring them. And his approach is, no, I'll do it in 6 days and I'll publish a paper. Fine with that. But yeah, the reality is you can spend a lot of time seeing where the problems are and try to think about what they mean. I mean, the devil is in the details.
All right. Well, we might wrap it up there. Thank you, JC.
Thank you very much for inviting me.